So today we are going to start a new chapter, which is scalars and vectors. So the chapter we are going to start is scalars and vectors and vectors. Even though the chapter is scalar and vectors, we are mostly going to talk about vectors since we learn about scalars a lot when we are in high school. So now we're going to learn about scalars and vectors. So first of all, when talking about scalar and vectors, let's understand what is scalar and what is vector. So first of all, the first topic that we're going to talk about is a scalar. So what is a scalar? So scalar, so those physical quantity that can be described completely with their magnitude only. So the important point is magnitude only. And for example, let's look at some examples. Some examples will be pressure, charge, current, 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 also current, sorry, um, current, time, amount of substance, as well as mass, length, etc., etc. So now let's go to vectors. Like this was it for scalars almost. We are going to talk about why these are scalars pretty quickly after we talk about what are vectors. Okay? So let's move on to vectors. Vectors. So the vectors, so those physical quantities that can be described completely completely with their magnitude and direction. And also they must follow the law of vector addition. So they have both magnitude and direction. And the next point, they must follow the law of vector addition. So the quantity should also follow the law of vector addition. So the law of vector addition. So this is another important point, which is they should follow the law of vector addition. Also, after that, let's talk about a few new terms related to vectors. So vectors associated with linear motion it might be better to write them in let's write it anyway. With linear motion, or linear motion generally means when we are talking about straight lines. So straight lines are polar vectors are polar vectors. So we are going to explain all these topics pretty quickly, don't worry about that. So let's highlight the term polar vectors. Let's make it blue color to say that it's a term, not that it's an important point. And the vectors associated with rotational motion are axial vectors. So axial from axis. So since stuff rotates about an axis generally, so that's it. Now let's look at some examples. Some examples of vectors. The common examples that you will find is velocity, acceleration, force, electric field, electric field, magnetic field, magnetic field, gravitational field, gravitational field, impulse, impulse, gradient, gradient of, gradient of scalar, gradient of scalar function, and some examples of axial vectors. So these were um, polar vectors. So these all of these are polar vector. Now let's talk about axial vectors. So the axial vectors are angular velocity, represented by omega. It's most common, you will find it in the formula of velocity, which is omega times r. Also, so this does not mean that velocity is axial vector, okay? It just includes the axial vector when we are talking about velocity and rotation, but it's different. Also, another one is angular momentum, which is represented by L. So this arrow sign means vector that we're going to talk about pretty quickly. And the most common formula that you will find it of it is R cross F. And also another term is torque, which is represented by tau. So basically like a T or backwards J. And the most common formula that you will find of it is R cross F. Okay, so now let's talk about each and every term that we studied. So the first one, let's talk about scalars. Let's talk, what are they? They can be described by magnitude only, which means they can be represented fully by a number only. So let's take a look at some scalars and understand why. So if I take some scalars, let's write scalars in the middle. Suppose one scalar that I know of is mass. Mass is a scalar. So if I talk about mass, if I say 1 kg, 20 kg, or any amount, you understand what that is, right? You get what I'm saying. Does it need a direction? It does not need a direction. Think about it. If I have a pointy shape, a 1 kg object, so suppose this is the object, even if I change its orientation, so let's actually use a shape for it so that it's going to be consistent. Let's take this right over here. Let's make this gray. So suppose this object is, let's make it 1 kg. It's 1 kg. Suppose I rotate this object. So I'm bringing direction into it. So if I rotate this object, is there going to be a direction involved with it? It's always going to be 1 kilogram. It does not matter with the direction. So it's independent with the direction. That's why mass is independent of direction. Okay, now let's talk about the things we had, which is pressure. So now these are the confusing ones. So let's first of all talk about pressure. Let's make it right over here. So pressure. So I hope you know what is pressure. So you might think that pressure has a direction. And yeah, it has a direction, but it does not follow vector algebra. That's why it is not a vector. If you remember, we talked about that the quantity should also follow vector addition, which is a very much important point when we are talking about pressure. So suppose, think there is pressure being applied by something. Instead of making this, let's make a block. Make a block. So here, suppose there is air outside and there is low pressure right over here. There is high pressure over here. Then you will feel that the pressure has a direction. So right over here, this will be that direction, this will be the direction, this will be the direction, this will be the direction. And you're not wrong. These are the direction, but this is not a vector because it follows normal algebra. Because so now let's talk about what is normal algebra. Think about it. If I have 1 kilopascal of pressure and I add another kilopascal of pressure, I will get 2 kilopascal of pressure. Even if I change all the orientation, it will always give me 2 kilopascal of pressure. Now, let's halt for a moment and go right over here. Let's take velocity. Let's take force. I think force will be much more easier. So now vectors. First of all, let's talk about force, since force is much more intuitive. Think about two forces. Think about two forces. Let's take a block. So take any object that is near you. So this is the object near me, suppose that. And there is a force. So this is a force. If I put this force, the object will move right over there, right? The object will move right over there. Suppose this is 1 Newton. Newton is the unit of force. If I kept another force in the same direction, and suppose this was, let's make this 0.5 Newton, then the net resultant will be 1.5 Newton in this case. So this is equivalent of saying 1.5 Newton is acting on the block. But this still does not describe it completely, because if you remember about vectors, we said that it must have magnitude and direction, and we are also talking about vector addition. So you might be confused. So wait a minute, we will get to it. So 1.5 Newton, but where? Suppose this direction, so 1.5 Newton left. There are also other ways to specifying the direction, but you must specify the direction, since suppose I had an object. If I have an object like this, if I move it up or there or there or there, it's going to affect it, right? It's not going to be the same. So now let's talk about vector algebra. So we must talk about the direction right over here. So coming back to this, you might still be confused. Why are we not talking about the direction in this? Like, there is a direction, there is a direction, there is a direction, there is a direction. I mean, I clearly understand it for mass. If you rotate it, you're changing the direction. It does not change nothing. But for pressure, there's a direction, and we're talking about vector algebra. So what is vector algebra? So we have this case. So we are going to take the same forces. We are not going to change the forces. We are just going to change the weight. So think about this. This is the forward force. This is the same force, but I'm going to rotate the force by 180 degrees and actually pull it right over there. So this is 1 Newton, this is 0.5 Newton. So take your object and pull it in one side and pull it in another side. If you pull it equally, it will not move, but we are not trying to get that case. Move it with one side with much more force, you will find that it will move in this direction, right? But will it move with the same speed? Not at all. It will slow down. Why? Because the effective force that will be acting on the block, let's move it a little bit down and to the side. The effective force that will be acting on the block will be 0.5 newtons to the left, since this 0.5 will cancel the 0.5 from this 1 Newton. So it will reduce. So this is what is vector algebra. So the direction can change the value. So the direction can change the value of your forces or your vectors. The values of vectors can be changed by changing the direction. So that's a very unique thing about vectors. And this is what I mean by when we are talking about vector algebra. Even though pressure has a lot of directions, when you're adding pressure, you always get the same pressure, right? Think about it. If I have 1 kg mass and 2 kg mass and I add them up, I will always get 3 kg mass. But if I have 2 Newton force and 1 Newton force, I may or may not get 3 Newton force. So it's not fixed. So it depends on something. But it depends on what? That's the real question that we're going to talk about. So it depends on the angle, which we will talk about in the next video. But now let's talk about where we are. So now we need to talk about charge. Charge is pretty simple. There is a positive charge and negative charge. So let's write charge. Charge. Charge is pretty simple. If you have one positive charge, so let's say you have plus q and you have plus q, you get plus symbolizes the charge, you will get 2 plus q. Pretty simple. That's it. That's basically what charge is about. If you subtract it, it's going to subtract. If you add it, it's going to be added. That's it. So suppose you add a positive charge. Let's write it down so that it becomes much more clear. If you add a positive charge to a positive charge, let's change the color so that it does not look confusing. You get twice the positive charge that you had. But if you add a negative charge to a negative charge, you get 2 times the negative charge. So a charge, but if you add a positive charge with a negative charge that has the same magnitude, which means they are equal charges but just opposite in sign, you will actually get a net 0. So I think this is pretty simple. Even though this might look simple right now, it gets confusing when you actually learn about charges. It's much more easier to understand this when you have not learned about charges. So now let's talk about another one. Let's go back. Another one is current. Current, most people also think that current is a vector, but it's actually a scalar. Think about it. If I have a current, suppose I make some wires. These are my wires. Looks like a river, so let's actually use something. Boom, 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 boom. So suppose I have this current as well as I have another one that's going to be pretty similar. But look, I'm making them overlap so that you can understand what I'm trying to express. So both are pretty similar cases. It's just that the direction has been modified a bit. So in this case, the angle between them, so this angle is lesser, whereas here the angle is more. Think that suppose there was a 1 ampere current flowing through this, and after going here, some current goes over here, some current goes over here. Similarly here 1 ampere, and some current goes over there, some current goes over there. But if you look at the current at this point, so if you add the sum of current at this point or at this point, it's always going to be 1 ampere, so it's always going to be 1 ampere, right? Why it's going to be 1 ampere? Since this 1 ampere current is divided, it must add up to 1 ampere. So you will learn more about them in current, but just understand that it's going to be 1 ampere. So even though I change the angle, so even if I change the angle between them, the value stay the same. So it does not matter with the direction, right? It does not matter if it has a direction or not. So it does not follow the law of vector algebra. I mean, it has a direction. Look at it. It's going right here. This is the direction of the current. And over here, this is the direction. This is the direction. This is the direction. And as you can see, the directions are different, which means the angle will be different. But still, it does not follow the laws of vector algebra, because vector algebra would say that these values would not add up to 1 ampere or will not be equal. It might add up to 1 ampere, one might, but the other might not, because the angle is different. So we talked about current, mass, pressure, charge. We have more, right? We have time and amount of substance. Now, finally, let's talk about time. Where can I fit this? Let's fit time right over here. So I'm going to move this part, quite hard to fit, but you gotta do what you gotta do. So let's put it right over there, make it much more smaller, and move it right up there. So now the final one that we're gonna talk about is time, and amount of substance is similar to mass. So basically think of it as mass. It's not the same as mass, but it works in a similar way. So if I had to explain why it is a scalar, I would explain it in a way that I have explained mass. So I don't think I will explain them. Okay? So now let's look at time. You might have heard time moves forward. So you might think time has a direction. And you might think the explanation that I'm about to give you is that time does not follow the law of vector algebra. That's why it's a scalar. That's not the case. There's actually, when we are talking about vectors, we are talking about direction in when we are talking about vectors, we are talking about direction in space. So we are talking about direction in space. But time, when we say time is moving forward, we talk about, it's talking about events. It's talking about events. It's not talking about the time, or sorry, it's not talking about the space. Right? So it's a bit different. So let's make it much more easier to understand. Let's take time. Suppose 1 second, suppose we talk about time, we say time moves forward. We say time moves forward. So you might think that this has a direction, but this does not have a direction. This does not have a direction in space. So think about it. Suppose this is space. Just suppose that this is space. If I asked you to show me time, you suppose you had a watch or something, you would say 1 second. Let's suppose you said 1 second. So if I asked you what would be the direction? I mean, would you say this? But what's stopping you from saying this? What's stopping you from saying this? Is there any effect that you can show that shows the direction? Like, no, there's no direction in space. So there's no direction in space. That's why time is a scalar. So when we are talking time moves forward, we are actually talking about order of events, not the direction of space. This and this are not the same. So I hope I cleared the misconception. And when we are talking about time, we are always talking about time intervals. So even though I said 1 second, it's actually talking about a time period. Suppose A from B took 1 second. You might have heard that our universe has existed for a long time, and there is a specific time which is about 14 billion years. Now the question might be, how do you know that it is 14 billion years? It's actually a time period between when it started, when it stopped, because we don't know when you are going to start. Suppose I said run for 10 seconds. I'm not talking about the time, I'm talking about the time interval. So when we talk about time, we are always talking about time interval. So I hope that was very much clear for scalars. Now let's move on to vectors. So we already have done for force, and velocity, acceleration, everything else will work the same. So right from here to here, everything is basically the same. Now let's talk about gradient of a scalar function. So a gradient, if you don't know what that means, so let's make it right over here and write gradient of scalar, was it function? Scalar function, yeah. Gradient of scalar function. So let's move it right over here and make the arrow. So when talking about gradient of scalar function, so I just made the gradient. So I just pause the video and make the gradient. So you might have, what is the direction of the gradient? Is it this? Is it this? So the direction of gradient is actually the direction from low to high value. So this will be the direction. Let's make it white and let's make it a much more deeper color, sorry, much more thicker. Let's make them thick. So right here, this is the direction of gradient. So in this case, it's from dark to bright, since the brightness increases. Since brightness, what's the spelling of bright? Brightness, spelling might be wrong, okay? Brightness increases. So gradient of a scalar function always goes from low to high. So that's the direction. It's low to high. That's the direction. So we have a direction for a gradient of scalar function. It also follows laws of vector addition. So that's why gradient of a scalar function is it's gonna be a vector. So now we talked about force. We talked about gradient of scalar vector. So if you look at them, they are always represented by straight lines. A straight line with the arrow, but they are always straight lines, right? That's why these are polar vectors. So these are polar vectors. Polar vectors. So these two are polar vectors. So now let's talk about sorry, I did not write here. It's axial vector. Let's talk about axial vectors. When we are talking about axial vectors, we are talking about rotation. So let's take this. We are going to take angular velocity, okay? So when talking about angular velocity, we are going to talk about angular velocity. So let's make them this. So when talking about angular velocity, we must talk about an object that is rotating. So axial vectors only come up when stuff are rotating. So let's take this thing and let's take a ball that is rotating about an axis. Let's take this ball. Should I make it another color? Why not? Let's make it orange. And suppose it's circling this axis right like this. Let's balance it. Okay, so it's rotating about this axis, right like this. So let's make this color white, and it's rotating, suppose like this. If it's rotating like this, the angular component comes right over here, and this vector, which has, it's, look at the direction of the vector. It's not a straight line, right? It's a curved line, which will be our angular velocity. So it's measured in radian per second. So if you look at this from the top, it will be a circle, obviously. And this ball, so this ball, if I copy it and move it and make it a lot more smaller so that it stays in scale. Suppose it moves from here to here in a certain amount of time, right? Then it would carve out a certain angle from the center. Suppose this. Suppose this angle is theta and the time is t, which will mean in this case the angular velocity will be theta by t. So theta will be measured in radians, so it will be radians per second. And we also saw that velocity was also involved in this. So the radius will be, obviously, the radius, I think it's pretty obvious. It's going to be the distance from here right to here. And the velocity, it's actually going to be this velocity. So the ball, the velocity of ball like this. Let's take another color. So this will be the velocity. Let's write t right over here. This velocity actually comes from omega r. So I hope that clears up everything, right? So this is a polar vector. Velocity is a polar vector, but angular velocity is an axial vector. The clearest way to see it is by the arrow. The arrow is rotating, it's an axial vector. If the arrow is straight, it's a polar vector. To remember, axial vector includes rotation. Axial means axis. In this case, this is the axis. That's why axial vector includes rotation. So with that, we are going to end today's video, In the next video, we are actually going to talk about the representation of a vector. So if you saw me representing vectors, it might be pretty clear to understand what is the representation of vector. But till then, bye bye.